No problem. So we are doing this analysis on functions. So Raghav, by the way, did you get a chance to look at the boards? Did you just have a look?
Sir, I couldn't understand.
Yes,
what was
yeah,
written.
yeah, right. Because and the way I write, and also it's a new topic. So analysis of functions. So I did say certain things yesterday, but today I will say them in an elementary language and only the things that we will essentially need. We will need essential to move forward. But today it will be more like sequence of functions. And over time, you will understand what is the goal of what we are trying to do. I will say it at some point over certain sequence of functions. So, I mean, let us just begin with an example. Okay, let me just say one word. So, what do we usually do? We take a sequence of numbers usually, and then we take its limits. We all understand that. Now we are going to take a sequence of functions and we are going to take its limits. Okay. How we are going to do that? Let us illustrate it through an example. It's better to do like that. Okay. So let me just take an example. This example is there in Rudin, from Rudin. And so here we have again a sequence of functions. Okay. So I don't know what is happening to the pen. Yeah. Okay. And we have the sequence of functions. So that is, let's just take this sequence, x1 minus, you see, sometimes it's not writing, 1 minus x square to the power n. And let us just take the domain to be 0, 1, close 0, 1. Okay. So then we want to take the limit. So can anybody tell us, those who were there yesterday, how to take the limit? I mean, what does this mean? What is happening? Okay, good, no problem. What does this mean? Come on, Adish and Satyam. So what do? We do it for points. Okay, we do it for every point, 1 point at a time. Okay. So how do? We say, okay, fix, because we want to reduce this. That's the only way we know what is happening. This penta is not working very well. Fix some arbitrary x naught. Fix an arbitrary, let's just say x naught, and you compute the limit, and then you find this limit. The cursor is suddenly going to the top of the screen and choosing some other option. I don't know why. F2, x naught, and so on. And you find the limit. You do this for every x naught, right? And then the limit. So what happens when you do it for every x naught? What kind of things you get will depend on what x naught you take. So please do the calculations and tell. Plug in the charger. Yes, what happened to the others? I mean, you guys were there yesterday, right?
Yeah,
Sir,
for
what is
0
go to
it will be
x?
0.
1 minute. Yes, Satvik?
Yeah, for 0 it's 0, and for 1 it'll be 1. Sorry, 0 again.
Uh-huh.
And other than 0 and 1, it'll be so 1 minus, so and raise it to a large number. It'll be 0 again. Okay, so it's 0 for all of them.
Yes. So let me write that first. So when you take 0, in that case, when you take the limit, every term is 0. So it obviously goes to 0. Is this clear, Raghav?
Yes, sir.
Sequence is just the sequence. There's just the limit of a sequence. Yeah. So that is all. I mean, just the most obvious way to compute limits, we do it. I mean, rather the only way, right? So far, right? We do that. So this is called pointwise limit. And if you take any, let's say, any half or anything, I mean, this also goes to 0, right? You can see that the powers of some number less than 1. And f of 1 is actually, I mean, f1 of 1 or I mean, any fi of 1. I just unplug and plug it. Okay, maybe I put this thing. Not needed. Yeah, and this is obviously. So the limit is again a function. Okay, it will be a function, right? Because we're taking a limit at every point, and the function is basically the function of limits. F, and what is this f now? I mean, f is 0. F of x is 0 for every x. Simple. Just what we have done is nothing. It is just to get used to this, and it's very important. This topic is something that is new. So you have to do a lot of calculations, a lot of practice first, depends on how much, to get used to get a sense of what can happen, and then you can prove still come. This is called pointwise convergence. In the practice stuff you have to do on your own. So you have to just pick any book, any analysis book and calculus book and see sequence of functions chapter and just do the practice. Pointwise. And please ask me if there are some interesting questions so that I can try them and try to do them. What is happening? Pointwise convergence. Okay, so this is called point. Okay. Taking the limit point. But then we introduced another type of convergence. Now, why we introduced and so on, let's not get into that now, because it's sort of a review and a bit of hands-on practice. We introduced another type of convergence, which is called uniform convergence. We maybe did not say that name yesterday. We said it, we came to it in a different way. We want to now discuss what is called uniform convergence. It's a more stronger type of convergence. The more real type of actually things have to be close for it to converge in that. Uniform word can uniform. So, uniform. Again, there is a very strong reasons for which why this convergence is introduced. Uniform. It's first time. No problem. So we have this thing. And so for this, what is the meaning? I don't know. What to do. So can anybody tell us the definition of uniform convergence? Adish. So if you have a sequence of functions, f1, f2, and let's say that it converges to f uniformly, then what does that mean? Or it has some uniform limit. Uniformly, it goes to some f limit. That will again be a function. Yeah. And what does that mean? So that means What does that mean? It means that, well, given it is just the definition of limit, okay, under a different kind of norm, but we won't use the word norm, just define it. Okay. See how it is similar to the definition of limit of ordinary. So given any epsilon greater than 0, again, there just exists a case. So this is a clear-cut, simple definition. There exists a case, okay, such that fnx minus f, again, these are real numbers, right? These are functions from R to R, 0, 1 to R. It can be from any subsetting type, doesn't need 0, 1. So these FIs can be from any subset. It needs certain things, but for now, let's just keep any. Right. Definition can be made for any subset, whether it will be interesting or not. This for all n bigger than equal to k and for all x. Okay. And that's the reason why we say uniform. That's the reason why we use the word uniform. It's uniform for all x. Just like uniform continuity is similar. If you don't know that or remember that, no problem. I'm not going to get to that now. But uniform is that thing for all x. And this one can introduce a norm, a different kind of distance between functions, so that this becomes exactly the definition of limit under that definition of function, under that notion of distance, when these functions are treated as points. Okay, so that's a very good distance because then it gives the same definition of limit of a sequence and it extends into this condition. But let's not.
Sir, your audio is not clear.
My audio is not clear, right? So do you think it's because of the connection or is it because of this microphone?
Now it's okay, I think.
So now it is clear?
Yes.
Yes, so it is because of this microphone. So, and there is a lot of hands. So let me change this thing. I'll just change I'll switch to a phone. One second.
So we can't hear you.
Okay, good. So I was saying something out of topic. So let me not say that. Let's come back to topic. So is this definition clear? Then we say that this sequence of functions converges to f uniformly. Okay. Now you can see that obviously, if this happens, if these FIs converge to this f, right, then this obviously implies that that what we did define earlier, the limit, this obviously implies that this limit fnx is equal to this f. Do you guys agree with this?
Yes.
Yeah, in fact, this is stronger, but this is certainly true, right? Because for each x, you would take the limit, and well, the limit will be fx. For each x, the limit of fnx will be fx because of the condition. In fact, more is true, but really, This is not always true, and it is a very important question for several reasons. We will come to slowly why it's important and when it happens, and some general conditions, sufficient conditions you can give for when it happens. Okay. So like if you can give some sufficient conditions under which it happens, so then or rather yeah, I mean some sufficient conditions and also some necessary conditions, rather I should say some implications. When this happens, then some other very good things happen. You can exchange limits, that's the main thing, and that in several implications there are there. And so when you cannot exchange limit, so then when those things, good things which are implied by this kind of convergence, when those good things don't happen, then it implies that the convergence is not uniform. So that will give us a method to prove convergence is not uniform. Okay, but so far we don't have any results. So we will just have to go by hand and do some practice. So let us just do 1 or 2 examples. Okay, I mean, let's just take the previous example and see if that convergence is uniform. Okay, so we know that if, so I hope the audio is more clear now. It should be very clear now.
Yes, sir.
Yeah, so I was not using this because this has lost its cushion. The cushion part is gone. So it's not uncomfortable, but I just got used to the other thing. I don't use the earphone anyways much, but yeah. This is just the first time in the day when I usually use it. Okay. So fnx is just this x times 1 minus x squared to the power n. Yeah. And we know that f is 0. The limit is 0, is a 0 function. I shouldn't really put x there, but just that we are used to. So far, we are not used to it. So, but the question is this uniform? Yeah. So please think about this. Let's try to do this now. I also don't know the answer. Let's think.
Sir, if you say epsilon is equal to 1, then
yeah, so take no, don't take equal to 1, because okay, let's see. I mean, you have to see whether it's right, whether it's a good thing or not to understand, right? So take epsilon to be 1, and let's see. Then what do we really have to consider? Take epsilon to be 1. Then what do we need? We want to see is that, I'm just writing it in words. Okay, is there a n or is there a k such that x 1 minus x squared to the n minus 0, because we know that the limit is 0. I mean, if there is a limit, then that limit has to be 0. We are just asking if it's a uniform limit, if it converges in the stronger sense. Okay, minus 0, so not right, is less than 1. Can you find a k? Well, there is nothing to find. It's always less than 1. That is just, yeah, less than 1. So epsilon equal to 1 is not, I mean, is okay, that is passed. That test is passed. We need to show that for any epsilon, the test has to be passed. For any epsilon, there has to be some k. It will depend on the epsilon, obviously. But take arbitrary epsilon, and now we ask this question. So this, you see, it just reduces to this very basic calculation in the end. We cannot always do this, but in these examples, we are doing this.
So like we can say that this is always positive.
What that x times that function fnx, those functions, they are always positive. That's okay. But is it, can you make them less than epsilon?
Modulus sign we can remove.
Oh, okay, yes, Oh,
And
that's
maybe
why.
then, yeah, and maybe then we need to find a condition on n, and it is hard in the exponential form, so we need to bring that n down. So maybe taking log of on the both sides might work.
Yes, so you can try that certainly. I mean, see, but remember that we do not have to explicitly find the n. You need to just say that there is such an n. But it's we should take the log and see. So you take log x. So we get this. Yeah, so let's see. I do not know if this is uniform.
So it the k will be dependent upon x also.
No, yeah, but we do not. We want to find a x. Sorry, I should say that we want to find a k such that this happens for all x. That's the whole
So
point.
it won't be uniform, right?
Why?
If it has to be uniform. No, but we can't find one for all x.
Why? Maybe
If
we can,
that
unless you tell us.
expression would be independent of x.
No. I mean, making it, see, because I mean, what if you can make n large enough so that it's always, no matter what x you take. So again, I should say that x is between 0 to 1. Sorry.
Okay, yeah.
Yeah, I should say that. I mean, that's why we said that it's a positive expression. Yeah. But now is it? Now it's more interesting. So this is just the elementary inequality question. Can you find n large enough so that this happens? I think I know, I have the answer a little bit. Rudin's example is slightly different. It has n square, and which makes it, but they solve a different problem, some integration related thing related to this. But yeah. So note that you do not have to explicitly define the n. You need to just see if there is an n such that this holds. There is a k such that this holds for, right, for all. Well, I mean, you need to just find 1k, because it's a decreasing. I mean, as you increase the n, it's a decreasing function, right? So there's no problem. So I'll just write that in the. You would have noticed this.
So perhaps, yeah, okay. So we can say
Yes,
we can
yes.
say that x times, so this LHS is less than x times 1 minus x whole raised to n.
So okay. Yes. So this LHS, I'm just writing here, is less than this. Yes,
Yeah,
that's
so
certainly
and
true.
this is 1 minus x
No. Why?
because that x square is like making no actually right.
It's
Yeah,
the
you're
other
right.
way, right?
Yeah, this is lesser than
Yes.
the,
And so what I was just saying is you just need to just find 1k for which this happens for all x, because then as you increase the k, it will continue to hold, right? It will decrease only, because 1 minus x square is less than 1. So if you multiply further by 1 minus x square, it will also be less than epsilon. So find some k. or show that there is some k. So that's all you need to do, but it should work for all x. Please, and also if the question is not clear, you should tell me, because this is a new topic. So yeah, that's why we'll do this example and then we'll join again. Okay, because there's some time limit is there, 45 minutes. So then we'll have again some short, maybe we can get some Cauchy condition thing in after this example. You see, this is an elementary question, right? So do something and find and say, like, is there some k?
Yeah, but we can obviously reduce this to like this is obviously less than 1 minus x square whole raised to k, right?
Right. But this is not uniform. 1 minus x square raised to the n is a problematic thing. You had seen yesterday a similar example, x to the n. That's a similar problem. So for 1 minus x square to the n, you cannot find k. Because you see, as you go very, very close to 0, this quantity becomes very, very big. Like what I'm trying to say, this so maybe it's a new for Raghav especially. So I'm saying this part only. See, this thing you cannot guarantee, you cannot manage. You take any n, you take any n, I can give you a x. How? I mean, this 1 minus s square is what? Some y to the n, right? I can give you a y. You take any, you fix an epsilon less than 1. You take any n, no matter how big you take, you can take an y. What y you can take? You can take y to be epsilon to the power 1 by n. And doesn't work. Basically saying that take x to be very, very small. So y is a little, close to 1. So this is not uniform, but multiplying it with x is uniform. So this approximation I will not go with. I mean, you see, right? It will not help because, or let's see. Okay, so let me just ask a simpler question and then this will be homework. This one will be homework, okay? Let me ask a simpler question. Let's focus on this one for a second. Sorry, so I have to just say it. So just focus on this one. So let's say that now the domain is 0 to some delta. This is the standard notation for this, so I'm using 0 to delta. Okay. Is now, and delta is less than 1. Okay. Is this convergence, I mean, you know where it converges point-wise, so that has to be the that's where it has to go. It goes to the zero function, not the zero number. The zero function, f equal to 0, means f completely 0, is this convergence uniform? Let's see. This idea has to be used in this. I mean, that's one way to do the problem. So let's think about this. So you can see it goes to 0 because you fix any x naught. See, when you want to find the limit, whether it's a uniform limit or not uniform limit, finding the limit is very simple. You pick every point and you find the limit. Now you can ask whether, now that limit will not change, whether it's uniform, not uniform, that's a different thing. Now you can ask if it's uniform, but knowing the limit can help you. So not maybe always, but in this case, you know what the limit should be. Now, whether it's uniform or not, whether it uniformly goes to 0. So let's see. So unpack the definition. If you're getting confused, then just unpack, do it definition wise and see.
So this becomes x bar n less than epsilon.
Yes, so it becomes is, so let me just write a little bit more. Given epsilon greater than 0, is there a k such that, well, let's write xk, because less than epsilon for all x in the domain. Can we manage this? Can we say that there is a k so that this is less than epsilon for all x in our new given domain?
Sir, kth root of epsilon.
Yes.
Because epsilon not is positive. I mean, epsilon is positive. Kth root is always defined. Let k be even or odd.
So whether it's right, so it is always defined, and then you
and it's always less than 1.
oh, kth root of epsilon. I know. No, you need to see the delta is given to you. You need to find a k so that it works for all x. Right? You see, the question is, can you find x? Can you find k so that for any x this is less than epsilon? Right? I mean,
Yeah, but the problem is x will keep changing. It needs to be true for all x.
Yes, for in 0 to delta. Delta is less than 1.
Yeah.
Yeah.
So feel like whenever you pick, say, some epsilon, okay, let's say 0.1.
Yeah.
We need to find k such that x bar k is less than 1 by 10.
Right.
So
but x is always less than delta, less than equal to delta.
Yeah, okay, so suppose k is the answer. Assume that k is the minimum.
Okay.
Okay, no, maybe minimum won't work.
Right.
No, I feel like up till some point x it will work, and then x plus 1 it might not work.
No, there's no x plus 1. It's only from 0 to delta. Okay, so please join again.
X plus some more value.
Okay, but if you can make delta to the power k less than 1 by 10, then you are done, right? Which you can. So yeah, let's meet on the other side. So just join again.